Good morning and welcome to our today's Let's Talk Science session. The two scientists will have a look at hybrid manufacturing today that should save 50% time and 80% material. So we're interested to know more about it. Especially, they will look at additive manufacturing technologies, which we all know that have gained momentum in the last years. Here, especially the DED technology, Direct Energy Deposit, or the second is wire arc additive manufacturing technology. And we all know, meanwhile, by a lot of demonstrations at shows and other sessions, the potentials of additive technologies, but nevertheless, it still needs trial and error to set up a stable process. And this especially when there is multi-material processes that are going to be used. And that's, I think, the major topic of today's session. The two speakers will show us methods that not only save time, but also mentioned in the title, would save material depending on the specific component geometry. The results that are presented are part of an ongoing research project called ADPROC-AD2, driven by the Technical University Vienna and the KU Leuven, the Catholic University Leuven. And the two speakers that will present the content today are Mr. Gernot Mautner, who is research assistant at the Technical University in Wien in the Institute for Production Engineering and Photonic Technology, and he is focusing on CAD/CAM solutions for hybrid processes. And the second is Mr. Syed Aref Banai. He has graduated in welding engineering at KU Leuven, and since 2022, he is also an academic research assistant and staff at KU Leuven in the field of sustainable materials management. So we are keen to hear about these results, and I hand over to the two speakers.
Thank you very much for the nice introduction. Yeah, a nice welcome to everyone who is listening in. EMO, let's talk science. Let's talk a little bit about hybrid manufacturing methods to optimize our traditional conventional part manufacturing. We split the presentation today between KU Leuven and the TU Wien for several reasons. One was we wanted to give you a little use case kind of already in preparation for what will be shown from various companies and research institutes at the EMO show this year. And the second topic is then a little bit more research, where we can definitely highlight how much work there's still left when we really want to go down that road and really want to implement additive technologies as a soon conventional part of machining. We have already been introduced. My name is Gernot Mautner from TU Wien. My colleague Syed Aref Banai from KU Leuven. We together designed the presentation and are your speakers today. And especially talking about additive manufacturing, we don't think that that needs a lot of introduction. I think in the last years, we all know how additive technologies ramped up in the markets. Various providers are in the market by now. And there are several different technologies to look at actually for various applications. For this presentation, already in advance, a little note, we focus a little bit more on the topics of DAD and wire arc additive manufacturing. So we are not talking a lot about powder processing for various reasons. You will see that in the presentation. But in general, a lot what we do here is not only for relativity space and NASA and a lot of big companies and institutes. There are a lot of advantages also for smaller companies and for a wider industry using additive manufacturing, such as typical ones, near net shape manufacturing instead of manufacturing from a big piece of material. You have new opportunities to combine material in specific regions. You have the opportunity to use special coatings when it comes to specific areas of your part that needs special functions. Or an important topic, especially obviously these days, sustainable production, energy efficient production, repair processes gain a lot of movement. So we try to use parts, components via repair services as long as we can in the value chain before we actually go back to the original road and start the full recycling processes of such a material. Yeah, very often parts are 80%, 90% working, but just a few features are worn off or are broken off, and additive technologies can help here. That a quick, fast repair service is keeping those materials in the loop. And these things we are researching currently in a project called ADPROC project, Advanced Processing of Additively Manufactured Parts. We're actually a consortium of several research institutes. In Austria, we have the FOTEC and the TU Wien IFT. Germany, we have the colleagues from Schmalkalden Machining Institute, from Stuttgart, as well as from Dortmund. And also Belgium is joining in the program with the KU Leuven and the Thomas More University of Applied Sciences. All of the funding and processes going on comes from the CORNET Collaborative Research Network and is handled then by various clusters and funding agencies such as the FKM, the EcoPlus Niederösterreich, and FFG, etc., or everybody who was participating or who is participating is here important to be known. ADPROC at 2, we had already a first project, the numbers indicating that, quite successful, focusing a lot on powder bed processes. The KU Leuven and TU Wien are now moving, as I already mentioned, more towards wire arc additive machining processes and looking into the manufacturing using those technologies. And especially here, I would like to show you a little use case that we did in our laboratories, and from where I also derived the title of the presentation. It's called hybrid manufacturing. Hybrid in that case means we combine additive technologies with subtractive technologies, which is one focus point in the CORNET research project at PROGAT2. So we look into, can those hybrid process chains have advantages when it comes to saving material, saving energy, saving process time, saving cost. All of that is a factor in there that we look into with some industrial partners that are also part of the research project. And just to give you a little insight, what are we talking about? Hybrid process chains. There are different versions. You see here one cell that was designed by TU Wien and is tourable in the facilities here in Vienna. You can see on the right a robotic welding cell from the company IGM, an Austrian company, and you have on the left side a machining center from the company EMCO in that case, and in between you have a robot who is manipulating the parts. So with such a cell setup and with the required cell controller and so on and the programs, we have the opportunity in general to run actually an automated process from a welding robot where the part buildup is happening to the machining center where you create actual the surface that you need then for your application. And obviously you can integrate, thanks to Industry 4.0 years, a lot of sensory tools in there. You can actually measure quite a lot what's going on in the process. Also interesting on the milling side, but especially for additive processes where still so much is unknown. We use a lot of sensors still to understand what's happening for specific geometries and specific materials, and Aref will show you a little bit more about that in a few minutes. That's the use case that I want to quickly go over with you, and it's actually a very nice one because it was at our university done by 2 students. One student was actually responsible for the design of this speedboat propeller, and the picture on the top right is actually the student in such a speedboat in the US. It's quite a hobby of him, and he designed a propeller that he needed for the races. And yeah, we had only conventional manufacturing technologies available, and then we said, why not trying something new? Why not trying for such a geometry maybe an additive and subtractive process combined, creating a hybrid machining process. And with that, we went into the machining cell and tried to make it happen. And you can see here a few insights from the programming side. We used Siemens NX CAD/CAM systems for both machining centers, including post-processors, etc. You need definitely a strong CAD/CAM system when you create those complex geometries. So interesting topic also in our research project, that we get actually the different manufacturers of robot welding cells also in that road, that traditional CAM systems are used when programming those movements. Yeah, and you can also see here in the middle that additive technologies is not only interesting on the part, but it's also interesting when it comes to the setup, yeah, where we use typical cylinders and then kind of added some features to mount the fixture on the plate of the machining table. So as you all know, a lot of creativity is needed and is wished when you talk about and use additive technologies. In the beginning, it was mentioned trial and error. And from my point of view, that's still very, very true. A lot of what research institutes are doing these days is trial and error handling of additive processes, trying to figure out what are the right process parameter combinations for certain materials, and also what's the right build-up strategies. You can see here our first shots on the propeller, really from a base plate. We developed too much heat, too much energy into the process, and the welding path was not working out. And we had insufficient bonding, we had a lot of holes in there, so that was not a strategy that worked. So we decided to actually create a basic cylinder done by a turning process, and we only weld kind of then the propeller plates then on the side to reduce the amount of energy and heat we put into the part. That worked much better, and I'm sure you know some other geometries and use cases in that direction. That's actually looking now very easy when you look at the videos. Still, there is a lot of work going into the trial and error phase. Still, there's a lot of work going into thinking about the fixture, about the process. And a lot of unexpected things are happening when you use such a hybrid process. So we're very happy that it worked in that specific use case. And I would actually like to highlight the results before I hand over to my colleague, which I think are more interesting for you at that stage, because that's quite significant. The material waste that we have compared to a conventional machining process where we would machine the part out of a full cylinder are obviously significant. Yeah? Removing all the material out of the cylinder is a lot of waste. Sometimes you can use the burrs and recycle them, reuse them, etc. But still, when we talk about recycling processes, you don't want to do that anymore in the future. You don't want to create a lot of waste that you then need to recycle in early process stages. All of that is effort, uses energy. Better is you don't have that waste in the first place, right? So a near net shape geometry is helping actually a lot. But it was also quite surprising, also when you combine the machining times. So a conventional machining on one machine, only the cylinder is done on the turning center, compared to a hybrid process, was also half of the machining time and providing therefore a lot of saving potentials as well. So it's not only that the chips can be reused, it's also that the machining of those chips in the conventional case just take a lot of time and create a lot of tool wear, and all of that needs to be taken into consideration. So when we're asking the question or adding something to our title for the presentation, we try to give you a strong statement. We try to motivate you looking into those technologies, look into use cases, rethink your current portfolio with additive technologies, various ones, and just really get creative when it comes to creating new options for your manufacturing chains. There is a lot to do. 50% savings was good, but there is still plenty of work and plenty of opportunities. And one very interesting optimization example in regards to multi-material processes is now demonstrated by my colleague Aref, and I would like to hand over now the word to him.
Well, thank you, Mr. Mautner, for your nice presentation. Now, I will give a specific use of our additive manufacturing in terms of multi-material deposition. This presentation would be a bit more technical, but I'll try to keep it interesting. In the next slide, I will tell you about the application and the issues regarding the manufacturing of multi-material parts. The applications mostly are used as corrosion protection for like pipes or pressure vessels in the petrochemical industry, which there is a corrosive environment, and also as transition parts in functionally graded materials. For example, in a bimetallic part, when we are moving from material A to material B, in between we will have a multi-material part which do the transition part in between to have a uniform property changes from material A to material B. There are quite a lot of issues for wire and arc additive manufacturing of multi-material parts. For example, when we use two different materials, there will be two different properties in terms of chemical and physical, like the melting point and also the fluidity of the material. And for each material, we need to use different welding or deposition parameters. So in this study, we tried to find a solution for these issues, which is one of them is a common consumables for two materials, and also a deposition strategy, which can be used as a guideline for manufacturing multi-material parts. In the next slide, I will give a short explanation of the principle of the process in wire arc additive manufacturing. The wire comes through a nozzle which is connected to a power source. It gets melted by the power of an electric arc between the substrate, between the plate and the wire, and there will be a shielding gas to protect the wire and the molten pool from the air. So three aspects of this process have quite a significant impact on the results. One is the shielding gas which is used, and the other is the stability of the arc, and also the shape of each bead that you can see on the bottom, which is the cross section of each layer in this process. Now, these three aspects have been investigated for multi-material when we are depositing two different materials next to each other. In the next slide, this is the deposition setup at KU You can see the two power sources, Fronius CMT power sources, which are both connected to a twin torch. This torch can handle two wires, as you can see on the right figure. And now we are using two different materials. And the deposition mode is sequential. Like, for example, first material A is deposited, and the material B is deactive, and then the torch moves the same path with deposition of material B. In the next slide, I will explain how we analyze the stability of the arc. So first, we want to find the common shielding gas for these two materials. As a test case, we used stainless steel and a creep-resistant steel. At the same time, in the deposition, we collected all the current and voltage data of the process using a data acquisition system. And then we compared two gases in terms of the different graphs in current and voltage. For example, the cyclograms shows, if you see at the black figure, you can see the difference between using gas A to gas B. For example, gas B has a more uniform, and also in the other figures, a clear difference has been shown that shielding gas can totally change the arc stability. Also, another representative of the arc stability is the amount of spatter produced during the deposition, and a clear distinction is shown between gas A and gas B. For example, in one of the gases, by using a few percentage of carbon dioxide, we could reduce the spatter quite a lot. In the second slide, in the next slide, yes, Next to the arc stability, we also check the beads geometry. For example, the uniformity of the beads height and width, and the variation of the dimensions, and also the cross-section of the beads to check the penetration. You can see from gas A to gas B, the penetration has been increased, and which can guarantee a good bonding between the material and the substrate, and also the bonding between each layer. This was for the arc stability and the shielding gas selection for two materials. In the next slide, I will explain about the deposition strategy. Yeah, to add one more thing, this result has been validated on a multi-layer component, which are the bimetallic walls. As you can see, using a proper gas, we could have a defectless walls, but the other gas resulted in a lack of fusion in the interface, which is not acceptable in the additive manufacturing. And also it has decreased the flatness of the wall, which means lower machining allowance, and that's how we can save material in the multi-material deposition. Okay, in the next slide, this is the deposition strategy when we are going to deposit two materials. When we are depositing overlapping beads, which has a common area, overlap area together, the offset distance between these two beads are quite important. For a single material, this has been done, and it's quite well known in the literature, and there are some models, but we try to find the optimum offset distance between in multi-material between two materials. When we have two materials, the dimensions of these beads are different, the properties are different, so we need a new model to find the optimum offset distance. In the next slide, if I want to show the significance of this distance, you can compare these two beads which have been deposited with a slightly change in the offset distance. On the left, you see when the second bead is deposited next to the first bead, the molten pool has been spreaded to the other side, and there is a large gap between bead A and bead 2, and this gap will remain in the further layers, and will result in a lack of fusion. But with a slightly change in the offset distance between these two beads, we can have a material flow from bead 2 to bead A to have a complete fusion. And this model, we try to find the proper offset distance, as we call it, critical offset distance, to have a optimum surface on top, and also a complete fusion between materials. In the next slide, this offset distance has been compared to the other models. You can see when it's two different materials, if you use the previous models, which are valid for the single material, on the middle and on the left, there will be a lack of fusion in between the materials, and we cannot get a acceptable component. But on the right, using the new model, we are successful to have a defect-free hull. And in the last slide, I will show some test cases. On the left, there are 3 valves to show the repeatability of this model, that all 3 has been deposited defectlessly, and also another structure, which we call it as a matrix or a chess structure, has been deposited using the same model by depositing material A, material B, and so on in each layer. This can prove that this model is valid to have a design guideline when we are going to deposit multi-materials. That was my last slide. I thank you for your attention, and if there is any question, you're welcome to ask. Dr. Schäfer.
Yes, I just switch on my mic. So yes, thank you for this very interesting presentation. As far as I can judge it from a technical perspective, very interesting, and it shows also the requirements that you have to take into account when going into these kinds of additive processes. My first question I receive here is what, because you were mentioning there is less time and less scrap or less material used. But could you give a statement on the cost perspective of this processes in single material or multi-material? Because this is always, or still is always, a question that classical production methods, cutting or whatever, maybe if you have larger parts, if you have a larger number of parts, maybe cheaper than the production per piece, cheaper than in additive.
Maybe I can answer that or try to answer that very interesting question. Actually, I cannot give you from our machining cell that kind of analysis. We're running currently a new use case with another with a company, so that would be then the similar use case but for a real part, and there we will for the first time really take into consideration also the machining costs, the depreciations and so on, and then we will actually have a very fair comparison, because there are also serial costs existing today given on a certain lot size, as you mentioned. Another thing that we want to look into is also the energy demand. So from an energy usage standpoint, how are those two process chains comparing? So that's another interesting aspect that these days need to be looked into. For an industrial company, I would also say it depends a little bit. You can buy brand new equipment, hybrid machines that have both functions available. That is obviously one side of an investment. If you imagine that most companies probably have already maybe some milling machines and maybe even have some even older robots that they use for certain applications, upgrading them to welding robots and then use them from time to time is giving you actually maybe a nice cost-sensitive process chain and machining chain that is not automatically going into too much money for the investment, and you cannot show the advantages anymore.
Okay, thank you. Well, what is your perspective? Is it more feasible that in, let's say, repair topics, or in, as you mentioned with the propeller, more complex 5-axis machining components, single parts or small batches, that this is a more valid perspective for these kind of technologies?
I believe there will be different niche markets for those kind of technologies. As repair was mentioned, that's definitely a big one. There is still a lot of manual welding going on in the different industries, just for the sake of not having something else available, maybe, especially when you talk about big products that are out somewhere on the field. And here, a cost-sensitive machining or robotic cell that has some smart sensors and can help you doing the repair process automated potentially. That's something there is a business out for that. We have partners in the project that are doing that, so that's something that is very real. For new part production, so not the repair application, I think that really varies a little bit on the supply chain needs. It might be that sometimes the conventional way is still maybe the better one to go when you have normal stable loads. But then at some point you might need some specialized tasks that only some specialized parts that only need a few changes, and you only need 3, but it's good money that you would get. And in those kind of situations where delivery time is maybe more important in a certain case, that could be something that you might look into. So I think there will be various scenarios, and I think additive technologies, especially those two we just presented, will be just a nice addition in for any metal manufacturing company in the future to have.
Okay, thank you. Concerning the multi-material deposition that you have shown as a pretty complex process that you have to take care of to have a good result. So would it always be necessary to have this gas analysis, for example, in the beginning, depending on the material you use, or is there already, or will there be kind of a knowledge base of combinations, material, gas, and all these things?
Well, actually, we have done this experiment for a certain pair of materials, as I mentioned, for stainless steel and creep-resistant steel, which have quite a lot of applications in the high temperature services and also corrosive environments. But this is not the exact result for this combination. Only this is the methodology that we have published. But in concern of other pairs of materials, we are actually working on a design guideline to give a more general guideline and more practical for the industry to how they can select the common consumables like shielding gas and also other aspects like the offset distance and deposition strategies. And there would be more easier and probably not to do all these data acquisition experiments beforehand.
Okay, let me see. I think so far, finally, my private interest, could you give one or two applications for this multi-material additive, so to have a better understanding, because what you have shown on your slides was, let's say, just a test situation, but what is a part that is to be produced with these multi-material concepts?
Yes, currently mostly in the chemical industries and petrochemicals, when there's a corrosive environment, instead of making a whole piece out of a corrosive resistant material like a stainless steel or nickel-based alloy, we can have a cheaper material for the whole body of the component and then have a cladding on it with the corrosive resistant material. Yes, in another study, part of the same project, we are investigating the feasibility of cladding Inconel on a low carbon steel for the same application.
Thank you. So as far as there are no additional questions, thanks for your very interesting presentation and thanks for listening. Of course, if somebody could not attend, please give them the information. It will be visible later on as well on the EMO website. And thanks for attending and all the best and have a nice day. Goodbye.
Thank you very much. Bye-bye.
Thank you. Bye.